Hey, welcome to the Explainer. We spend so much time looking up at the stars, but today we're going down, way down, deep into the heart of our own planet to answer a pretty simple question.
It's kind of crazy when you think about it, right? We have telescopes that can see back to the dawn of time, but the very ground we're standing on, well, it's pretty much a total mystery. We've never actually seen what's inside the Earth. So, how do we have any idea what's down there?
Okay, get this. The deepest hole humanity has ever drilled, the Kola Super Deep Borehole, only goes down about 12 kilometers. And yeah, that's an incredible engineering achievement, for sure. But in the grand scheme of things, it's barely scratching the surface.
And I say that because this is the distance to the center of the Earth, over 6,000 kilometers. Our deepest dig doesn't even get us 0.2% of the way there. So, what in the world is filling all that unexplored space beneath us?
Well, scientists have pieced together a picture, and it turns out the Earth is structured kind of like a giant onion, with 3 fundamental layers. So let's peel them back one by one.
First up, you've got the crust. That's our home turf, the layer we live on. It's the thinnest outermost shell, made mostly of silicon and aluminum, which earns it the nickname CHSL. And it's not all the same either. It's split between the thick continental crust that makes up our land masses and the thinner but denser oceanic crust that lies beneath the seas.
Okay, right below the crust you hit the mantle, and this thing is an absolute monster. It's a huge layer, stretching down nearly 2,900 kilometers. It's mostly made of silicon and magnesium, or SEMA, and get this, it's not just a solid block of rock. Parts of it are semi-molten and can actually flow, kind of like super thick tar over millions of years.
And finally, we arrive at the core, the engine room of our planet. This is made of heavy metals, mostly nickel and iron, earning it the name knife. Now, the core is split into 2 really important parts, a churning liquid outer core, which generates Earth's protective magnetic field, the shield that deflects deadly solar radiation and makes life on the surface even possible. And inside that is a solid inner core. So you might be wondering, wait, if it's hotter, why is it solid? And the answer is just insane pressure. The weight of the entire planet is pressing down, squeezing it so hard it literally can't melt.
Now, to really put that into perspective, just look at this. The crust, our entire world, everything we see and know, makes up just 1% of the Earth's volume. Just 1. The mantle, on the other hand, makes up a colossal 84%. That's the real bulk of our planet right there.
But, volume is only half the story. The core, even though it's smaller, is made of that super dense iron and nickel, so it punches well above its weight, accounting for nearly a third of our planet's total mass. This layering by density is pretty much the fundamental organizing principle of our entire world. Okay, but here's the thing. These layers aren't just sitting there. No way. The way they interact is the engine that makes our planet so dynamic, constantly building and rebuilding the world we see.
And this is where it gets really interesting. The crust and the very top, solid part of the mantle, they form this rigid shell called the lithosphere. But this solid shell isn't static. It's actually floating on a weaker, semi-molten layer below it called the asthenosphere. Just try to picture it. Giant rafts of solid rock, floating on a sea of super hot, slow-moving tar.
And that simple idea is the foundation of plate tectonics theory, proposed by Mackenzie and Parker. Our entire world's surface, the lithosphere, is broken into about 7 of these major plates, with the Pacific plate being the biggest. And these plates are constantly shifting, crashing into each other, pulling apart, and sliding past one another. This movement is the engine that creates everything, from the Himalayas to the Atlantic Ocean.
So this all brings us back to our original question. If we can't drill down there, how do we know about the liquid core, the flowing mantle, and these massive plates?
The answer is actually surprisingly elegant. We use the Earth's own internal rumblings. Every single earthquake sends shock waves, or seismic waves, rippling through the entire planet. By listening to these waves on the other side of the world, we can create a sort of planetary ultrasound and figure out what they traveled through.
Now, there are 2 main types of these waves. You've got P waves, or primary waves. They're the fastest. They're compression waves, kind of like sound, and they can travel through pretty much anything, solids, liquids, and gases. Then you have S waves, or secondary waves. They're slower, they move up and down, and here's the absolute key detail. S waves can travel through solids, but they are stopped cold by liquids.
So you have an earthquake on one side of the planet, and you set up detectors on the other. What do you think happens when those P waves and S waves hit the planet's core?
And this is the breakthrough discovery. The P waves, they punch right through the core, though they get bent and slowed down a bit. But the S waves, they hit the outer core and poof, they vanish. They simply cannot pass through. This creates a massive shadow zone on the opposite side of the Earth where no S waves from that quake are ever detected. That's the geological smoking gun, the undeniable proof that our planet's outer core is a vast ocean of molten metal.
I mean, it's really a fantastic piece of scientific detective work. By piecing together clues from all these different sources, we've built a coherent map of our planet's interior. In fact, geologists have become so precise that they've mapped the specific boundaries, or discontinuities, where seismic waves abruptly change speed. Each one of these, like the famous Moho discontinuity between the crust and mantle, or the Gutenberg discontinuity between the mantle and core, marks a fundamental shift in the material deep beneath our feet.
So to summarize, our knowledge comes from two kinds of sources. We have direct sources, like analyzing magma from volcanoes or rocks from deep mines, which give us actual samples of what's down there, even if it's from relatively shallow depths. But the deep picture comes from indirect sources. Those seismic waves we just discussed, our planetary ultrasound, studying meteorites, which are like leftovers from planetary formation, and measuring subtle changes in gravity and the Earth's magnetic field.
And that really is the essence of it. We can't see inside our world, but we can listen to it. By interpreting the echoes and vibrations from deep within, we've managed to map out a hidden landscape that's more alien and extreme than the surface of any other planet in our solar system.
It makes you wonder, doesn't it? As our instruments get more sensitive and our understanding grows, what other profound secrets about the very ground we stand on are just waiting to be discovered? What else is the Earth trying to tell us?